Hello, I'm Jay Scott, an editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series, providing information to journal readers and others about technology for industry professionals. ASHRAE does not review supplier webinar presentations. Mitsubishi Electric Trane HVAC US presents today's webinar, Applying VRF Systems in Cold Climate Applications. Today's presenters are James DeBerry, Commercial Marketing Manager, and Mike Machemehl, Senior Manager, Commercial Channel Strategy. James develops and executes marketing plans for commercial new product launches and existing product maintenance on behalf of Mitsubishi Electric Trane. With extensive corporate marketing experience, James most recently served as Senior Marketing Manager at AT&T Atlanta. Mike is part of the team that creates sales, marketing, and channel development plans for the commercial markets in the U.S. for the City Multi-Commercial VRF product line. Mike is a registered professional engineer in the state of Ohio, a certified energy manager, a lead green associate, and has over 30 years of experience in the commercial HVAC market. And now we turn the presentation over to James. Thank you.
All right, thank you very much, Jay. Hello and welcome to today's webinar entitled Applying VRF Systems in Cold Climate Applications. On behalf of Mike Machemehl, I'd like to thank you for the time you've chosen to invest in today's session, and we think you'll find the content presented to be quite valuable. We're planning to spend about the next 45 minutes discussing VRF, or Variable Refrigerant Flow technology, and we'll have some time at the end for questions. And we'll also explore some solutions for today's commercial marketplace and how they perform in cold climates. Here you can see the learning objectives for today's webinar. They include: describe how modern VRF systems perform in cold climates, design systems to solve derating challenges and recognize when to apply flash injection technology and water source VRF systems, design and install systems with precautions for snow and cold weather, discuss how applying VRF technology supports strategic electrification and decarbonization in cold climates. Mike and I look forward to sharing our thoughts on VRF technology and some of the characteristics and advantages it offers for cold climate applications. We'll also look at a couple of successful case studies, and we'll share some additional resources for continued learning at the end. We'll have time at the end of our presentation to address as many questions as possible, so be sure to submit your questions throughout the webinar using the Q&A function within the presentation interface. With that, let's get started. I'd like to spend a little bit of time talking about what are VRF systems. VRF systems heat and cool zones by moving conditioned refrigerant through small diameter piping. VRF systems are electric powered and do not require fossil fuel combustion to generate heat. These can be heat pump or heat recovery systems. Heat pump systems are used for single zone applications or multi-zone applications that follow the same thermal profile. On the other hand, we typically install heat recovery VRF systems, which use a branch circuit or BC controller to provide simultaneous heating and cooling in multi-zone applications with diverse thermal footprints. For example, hotels, office buildings, and any facility where some zones will require heating while others require cooling, all in the same building. So let's break down those systems that I talked about. At its most basic, a VRF system consists of an outdoor unit and a network of indoor units connected by refrigerant lines and governed by controls and sensors. VRF heat pumps are effective when all of the building zones can be in the same mode at the same time, either heating or cooling. The outdoor unit contains a compressor, condensing coil, reversing valve, and condenser fan. Each outdoor unit may be connected to multiple indoor units, and individual outdoor units may be combined to increase tonnage. Each indoor unit contains a fan, filter, heat exchanger, and temperature sensors for the refrigerant and return air. Indoor units may be ducted, for example, concealed horizontal ducted units, also air handlers are another example, or ductless, like wall-mounted, floor-standing, or ceiling cassettes. So in this example you see here, you can see the outdoor unit on the left with refrigerant piping running to a variety of indoor units. And by the way, each outdoor unit has the ability to connect up to 50 indoor units. Each zone can have its own indoor unit that provides cooling and heating. Outdoor units capture heat from the outdoors that is transferred to indoor units during heating. Outdoor units reject heat transferred from the indoor units during cooling. With heat pumps, indoor units are either in all cooling mode or all heating mode. So in this example that you see here, we're showing all the indoor units in heating mode. Heat recovery VRF systems, on the other hand, offer cooling and heating simultaneously within the same system. As mentioned earlier, VRF systems with heat recovery are the ideal choice for office buildings, hotels, and any facility with diverse comfort needs that might require some zones to be heated while others are cooled. One example of that might be an office building that gets a lot of morning sunshine. In that example, some of the areas of the building might need to be cooled, whereas if the other side were still in the shade, those areas of that building might need to be heated, for example. These systems use a branch circuit controller to direct refrigerant based on the conditioning needs of a particular zone, either heating or cooling, as we discussed. So how does this work? Well, one way to look at the BC controller is like a quarterback or a decision maker. By using a liquid gas separator, the BC controller separates the refrigerant so that some areas are cooled and some are heated. So each area or zone has its own indoor unit that provides heating and cooling. So here again, you can see the outdoor unit on the left connected to refrigerant piping with the BC controller, which is that box just to the left of center, connected again to a variety of indoor units. But you can also see with the depiction of the blue and red lines that some areas are in heating mode while some areas of the building are utilizing cooling. So in the other example, so instead of all indoor units being in one mode, a heat recovery system is capable of simultaneous heating and cooling. So let's talk a little bit about the compressor advantage of VRF systems. Each VRF outdoor unit has an inverter-driven compressor, enabling the system to more successfully handle part load and low load conditions compared to conventional HVAC systems. The system only uses the precise amount of energy to meet the desired set point. The VRF system keeps occupants comfortable at the set temperature they choose, even as environmental conditions change. This efficient approach reduces monthly energy bills and increases occupant comfort. Heating and cooling loads continue to get lower as passive house and other methodologies improve building envelopes and increase overall efficiency. Conventional systems use a fixed speed compressor which cycles a unit on and off whenever the room dips below desired temperatures. That's depicted here by the black dotted line. This type of system relies on an all or nothing approach, with the compressor running at either 0 or 100%. This can lead to unpleasant temperature swings as the system strains to maintain a constant temperature. Inverter compressors, on the other hand, are always running in the background, adjusting the compressor and modulating the speed in real time. That's represented by the green line. By ramping up power to the compressor when needed, an inverter provides a more accurate, on-demand approach to temperature control. If your room temperature is already a comfortable 72 degrees, for example, an inverter may slow the compressor's engine to a crawl. If your room is really warm, say 85 degrees, the inverter will push the compressor into high gear, reducing that temperature more quickly. This is another source of energy savings, as this eliminates the energy-intensive start and stop cycles of conventional HVAC systems. As you can see here, there are a variety of indoor units from ducted to ductless, or they can be used in combination. VRF equipment is very compact, saving space and offering a variety of aesthetic choices. Here, for example, you can see the ceiling cassette, the ceiling concealed ducted unit, a wall-mounted unit, the air handler, and the floor standing unit. VRF control software can integrate with non-proprietary platforms such as Tritium's Niagara 4 framework for advanced sequences and higher-level building automation systems control. VRF controls can integrate with third-party systems through standard protocols like BACnet or Modbus. This allows for centralized control and even more insight for facility managers. Now let's talk a little bit about going beyond the mechanical bid. VRF installed costs has come down significantly in recent years. However, first costs can sometimes be an obstacle to installation. If you look exclusively at the mechanical bid, that certainly becomes feasible. A developer or building owner seems to pay a premium to install VRF systems over a VAV or other conventional systems, for example. But if we look at going beyond the mechanical bid and how the characteristics of HVAC systems affect the cost for other components of the building like plenums, ductwork, and structural steel, we start to see how even the first costs of VRF systems can be competitive with less energy efficient alternatives. For example, eliminating the need for long runs of ductwork. If we take an even more comprehensive view and look at life cycle costs for things like maintenance and energy bills, we start to see how the value of a VRF system can far exceed alternatives. If you've been following the news and developments around strategic electrification and decarbonization, you've likely come across information about carbon reduction initiatives across the country. Some of these are driven by state and local governments and city governments. In New York City, for example, Local Law 97 sets limits for the metric tons of CO2 a building over 25,000 square feet can produce per square foot. Building owners will be fined if their CO2 level emissions exceed the limits for their category. Fines in New York City will equal $268 per ton of CO2 above the allowed threshold. In other areas, state and city governments, even utility companies, might offer incentives for a building owner to install VRF systems. Massachusetts, for example, has been a leader in this area. Let's talk just a little bit about the growth in the VRF category before I turn the presentation over to Mike. VRF was introduced into the United States over 15 years ago after many decades of prominence throughout the rest of the world. In fact, in Europe, it accounts for over 80% of the HVAC market. VRF systems are widely recognized by decarbonization advocates, policymakers, and interested members of the public as essential to decarbonization and moving to cleaner electricity for the built environment. We can see this in the studies and reports produced by organizations like the Northeast Energy Efficiency Partnerships and the Vermont Energy Investment Corporation. The chart that you see here on the screen is from NEEP's Variable Refrigerant Flow VRF Market Strategies Report and depicts how NEEP sees the adoption of VRF systems as a primary heating and cooling system for commercial and institutional buildings in the Northeast and Mid-Atlantic. The green line showing market penetration of over 40% by 2030 is the outcome NEEP and other electrification advocates are working toward. In any case, VRF adoption will continue to increase, and this creates opportunities for the HVAC contractors and engineers who have built expertise and experience with the technology. Now that we've explored VRF technology, I'll turn the presentation over to Mike, who will go into more detail about designing VRF solutions for cold weather applications. Mike?
Thank you, James. We're going to talk about several design approaches that we've seen used over the years for addressing cold weather climates. If we look at design objectives of a building of reliable comfort, resiliency, and energy efficiency, none of those things would mean very much if we couldn't adequately heat the building on the coldest winter day. The good news is that VRF is to the point where we can heat the building in the coldest of climates, even including ASHRAE Climate Zone 6. If we look at heat pump technology from 20 years ago or more, we found that the heating capacity dropped off pretty quickly, started derating around 40 degrees Fahrenheit. And by the time you got to about 25 degrees Fahrenheit, you had really very little heating capacity, and usually would just, at that point, lock out the condensing unit and turn on some auxiliary source of heat, usually electric strip heat, which is a fairly inefficient way to heat the house or the building. So we'll talk about some specific approaches to solving derating challenges. We still have to follow the laws of thermodynamics as it gets colder out. Generally speaking, capacity and efficiency of heat pump systems, including VRF systems, drop. But we'll look at the specifics of that. And as shown on the screen here, here's some approaches that we've seen used. First one, flash injection technology. Second one is auxiliary heat. Then we'll talk about sole source sizing based on the heating load. And that's simply just oversizing, if you need to, your condensing unit such that you can meet the heating loads. Number 4, oversizing the DOAS heat. Most of these shown here are mutually exclusive to each other, with the exception of number 4, oversizing the DOAS heat. That's one that can be used in conjunction with some of these other approaches, and we'll see why when we get to that part of the presentation. Number 5, install outdoor air-cooled units inside the building. And then lastly, install water source VRF systems. So let's talk about those one at a time. Flash injection technology is a technology that's offered by many manufacturers. Some manufacturers have a purpose-built piece of equipment for extremely cold weather climates, like Mitsubishi. Some manufacturers integrate this into their standard product or a variation of flash technology into their standard product. But the way it works is essentially as it gets colder outside, we have to overspeed the compressor to capture more heat from colder ambient air. And there's limitations to how much we can overspeed that compressor. If we just oversped the compressor and didn't do anything else, the heat and friction buildup would cause the compressor to fail. So essentially with flash injection technology, what we're doing is injecting some gas liquid mixed phase refrigerant into the shell or the dome of the compressor to basically remove that excess heat so that we can overspeed the compressor without burning it up. If we look specifically at what's going on, I'm not going to go through the whole diagram for sake of time, but I will walk through a couple of points. On the right-hand side is shown the evaporator coil in the heating mode. The refrigerant is traveling in the downward direction through the LEV shown at point C. LEV stands for linear expansion valve. And then the refrigerant at that point goes to a gas-liquid separator at point D. Liquid coming off the bottom at point E, and then gas coming off the top at where it's shown the dotted line. The liquid then travels through another linear expansion valve shown at point E and through a heat interchanger circuit where it's actually absorbing heat from the other hot gas that was coming off the top of the gas liquid separator. And then that goes up and through another linear expansion valve, LEV4, where we're metering that mixed phase refrigerant into the dome of the compressor. So we only put as much in there as we need to do as much cooling as we need so that we don't cause that compressor to overheat. So that's essentially how the flash injection process works. We're metering a mixed phase refrigerant into the dome of the compressor to cool it down so we can run it at higher speeds without causing any sort of failure in the compressor. If we look at performance, the Mitsubishi purpose-built piece of equipment that we have performs all the way down as low as 31 below 0 Fahrenheit. We rate that unit down to 22 degrees Fahrenheit below 0. The standard equipment, for the most part in the industry, manufacturers will rate to about 13 below 0 Fahrenheit. So you can see that this is not the technology from 20 or 25 years ago where you had to turn it off at 25 degrees Fahrenheit. We're operating well below 0 with significant heat output at those lower temperatures. Moving to option number 2, this is an auxiliary or backup heating system approach. We see this used in buildings where that infrastructure is already existing and somebody wants to add a VRF system. Maybe they're adding air conditioning to a school that didn't previously have it. And that infrastructure is there. If it's in good shape, maybe it makes sense to leave it in place and take advantage of it and use it as a backup system. Most commonly, we see the VRF as the first stage of heat, and then the auxiliary or backup heat will end up being the second stage of heat, just for efficiency reasons. You want to run the system in the most cost-effective manner, and usually this is the most cost-effective order in which to do the heating. Sometimes in larger cities, we do see district heating, maybe district steam heating or district hot water heating. And in that case, we do have the opportunity and the ability to run VRF as the second stage of heat and the district heat as the first stage of heat. We're going to talk about two methods for energizing auxiliary heat. Auxiliary heat can be either electric or hot water or gas, really any source of heat. It can be duct coils mounted downstream of a ducted air handler, either electric or hot water. It could be baseboard electric wall fin radiation or baseboard hydronic wall fin radiation. So this takes on a number of different ways what the auxiliary heat can look like in a building. If we look at the first method, we're going to do that by basically a drop in space temperature. And this is a space-by-space method. In other words, each space is operating independently. Some spaces may not even have auxiliary heat. You may only have it in critical zones in this approach. But essentially what we're doing here is as the temperature drops, we start out at 0.1 where temperature is at set point, and then it's dropping to 0.2 as shown. And at that point, we have auxiliary heat is going to kick in at some predetermined temperature. We want to give the VRF heat a chance to heat the space. So you don't want to engage auxiliary heat too quickly. So we want a little bit of a deadband there of about 2 degrees. But then we can set that auxiliary heat to kick in anywhere between 2 degrees and 9 degrees Fahrenheit below space temperature. So if you have a set point of 72 degrees, you might kick the auxiliary heat on 3 degrees below that, say it's 69 degrees. Or you could let it drop a lot further and go all the way down to 63 degrees. So at 0.3 in this example, at 4 degrees below our set point, we're engaging the auxiliary heat, and then the temperature starts coming up, and we get all the way back to 0.4 and then 0.5, where we turn the auxiliary heat off and then just rely on the VRF heat pump heat at that point. So that's our space-by-space method. We also have a method to do it, we call this the global method, where essentially instead of doing each space standalone, we're doing the whole system as one system. So we're switching the entire VRF system over to auxiliary heat. And a good example of this is, I mentioned earlier, a school. Maybe a school has boilers and hot water unit ventilators, and they're adding a VRF system for cooling. Maybe it makes sense at, say, 15 degrees to just switch the whole system over to the backup boiler system, fired by a natural gas-driven boiler. So we can see here that we have, in this case, our outdoor unit is running down to point C, which in this example is 14 degrees. And then between 14 degrees and -4, we're actually running both the outdoor unit, VRF condensing unit, and the auxiliary heat together. And then once we get below point A, or 4 degrees below 0, we're only running our auxiliary heating system. So very important, if you're taking this approach, you want to make sure that, number one, you have all of your zones covered, since you're turning the VRF system off at a certain temperature. And also you want to make sure that the auxiliary heating system is sized for the entire heating load of the building. So two very important considerations. When we reverse the cycle and the temperature outside is rising, we just reverse the sequence that I described before. However, we have 2 different trigger points now. Instead of triggering at point C and A, and as temperature is falling, we're triggering at point B and D, or in this case, 8 degrees Fahrenheit and 20 degrees Fahrenheit. Just a little bit of a summary. I'm not going to go through each of these. Method 1, the space-by-space method. Space temperature, it has to drop. By definition, you have to be deviated from set point for that to engage. So if you have that deviation set at, say, 9 degrees below set point, you might get some comfort complaints at that point. So you want to give some thought to where you set that as far as when that auxiliary heat kicks in. With method 2, or the global method, we're switching based on ambient temperature. So the space may or may not see any degradation in temperature as it's getting colder outside. In other words, you might switch it before you have trouble keeping up from a heat pump heating standpoint. Zone operation, I mentioned earlier, method 1 is independent, so we can put auxiliary heating coils in only our critical spaces. We could also do that in all the spaces. Doesn't necessarily have to be only in some spaces. Whereas method 2, we want to make sure that we have all of our zones having backup heat. Also with method 1, we want to make sure that we don't size our heaters too big. We've seen this on ducted units where we have a downstream electric heating coil, and if that heating coil is sized for too big a delta T, because you're running the heat pump heat and the auxiliary heat in series with each other, you have an additive delta T. So if your heat pump heat is giving you 20 degrees delta T and your electric heaters are designed for 30 degrees delta T, you're going to have a 50-degree delta T coming off that unit, and that could be problematic. So we always advise design engineers to size the heaters in method 1 for the difference between what the VRF unit is doing heating capacity-wise and the space load. How often will the auxiliary heat run? If you're using flash injection technology, probably not much, if at all. Matter of fact, we see very few designs where people are using the flash injection product and also putting in auxiliary or backup heat systems. Most winter days only require part load heating. We'll see that here on the next screen. So this shows the number of bin hours in some of the major cities shown. For example, Chicago has about 4,000 hours between the ambient temperatures of 50 degrees and 80 degrees Fahrenheit. So we have to size our systems, both for heating and cooling, for our worst case winter day and our worst case summer day. However, we operate at those points less than 1% of the time. This is really where we're operating most of the time. So we want to make sure that the system is energy efficient at these points. And that's where VRF system shines, is at part load. And we can see there's a lot of part load hours even in colder climate cities such as Chicago. Option 3 is similar to option 1, using the flash injection product, except we're just doing this with the standard product now and oversizing such that we have the required heating capacity that we need. And this is generally done in climates that get cold, but not as cold as places like, say, Chicago. So when we do this, we need to make sure that we look at the heating D rates. You can either use the charts, which is getting rarer and rarer for people to use the engineering manuals and the D rate charts, or what's most common now is people use the manufacturer's selection software to rate these. So you can build these units in an as-configured basis and look at actual heating D rates and cooling D rates based on your design temperatures for both winter and summer. The other thing we want to make sure to do in heating design is to look at the supply air temperature on your design winter day. That was a complaint with older heat pump technology, is that the units didn't make very warm air. You know, maybe it was able to keep up with the thermostat, but the discharge air was 78 degrees, and people just felt cold. Well, now with VRF technology, it's quite common on your design day to have discharge temperatures in the mid-90s and higher. I personally like to see a supply air temperature on my worst case winter day of something close to 90 degrees. Depending on the type of space it is, some spaces would be more sensitive to that than others. You know, you might be able to get away with a little bit less. But you want to just make sure you're looking at your supply air temperatures, and that's shown as an output on the manufacturer's selection software. You can look at supply air temperature at given conditions. If we look at an example, we have a university building that we're designing a VRF system for. Its winter design temperature is 5 degrees above zero, 5 degrees Fahrenheit. And our total heating load for this system is 120 MBH. So which model of the following one shown would satisfy the heating load at 120 MVH? Outdoor unit 1 option, we get a nominal heating output of 188 MVH. Outdoor unit number 2 option, we get a nominal heating output of 160 MVH. And outdoor unit number 3 option, we get a nominal heating output of 135 MVH. Now bear in mind, nominal heating output is at 47 degrees ambient, 47 above zero. So we want to make sure that we have the heating capacity we need at 5 degrees. Well, if we look at the heating derate charts, and like I said earlier, most people are going to use the software to determine this, not actually pull out the manuals, but there still may be some people that would do it this way. If we look at 5 degrees, and we can see that the heating output goes down as we go to the left, in other words, it's getting less as we get colder, we can see that we have a heating derate at that temperature of about a 0.65. So our nominal heating output at 47 times 0.65 gives us what that unit will do at 5 degrees above zero. And if we do the math, we'll see that that ends up being the largest unit shown, the one that was 188 MVH. If 188 times 0.65 equals approximately 120 MVH. As I mentioned earlier, I want to make sure that we oversize, if we're using this approach, not just the outdoor unit, because we can run into a situation where if our indoor units haven't been bumped up in size, the outdoor unit has more capacity, but the indoor units really can't pick it up, so to speak. So generally, you're doing both the indoor units and the outdoor units. And I always counsel engineers when they're using the selection software to look at it as an iterative process. Make a selection, look at the capacities, look at the discharge errors, go back and tweak it a little bit, play around with sizes. Maybe you bump a few indoor unit sizes up or bump the whole system size up. But look at it as an iterative process as you're designing to make sure that you're happy with the end result. As I mentioned earlier, oversizing the DOAS heat is one that can be used in conjunction with these other ones if you have a DOAS system design, dedicated outside air system design. Oftentimes, the DOAS system is designed to provide room neutral air, so air between, say, 70 and 75 degrees Fahrenheit to the space. What's pretty easy if you have a DOAS system and pretty low cost to upsize that heat and then put in a recirculation air damper such that in the dead of winter, if you needed it for an emergency, or if you wanted to do some sort of morning warm-up or daytime warm-up cycle, if you have oversized the heater, so maybe instead of putting a 400 MVH heater, you put in a 600 MVH heater, and you know that if you close that outside air damper, open the recirculation air damper, drive the unit to full heat, you can get discharge air temperatures, maybe 100 to 115 degrees Fahrenheit coming off that unit. You can provide a lot of heat quickly to all the spaces that are served by that DOAS unit. Pretty easy to do. In the Midwest, most of the northern climates use gas heat for the heating source in DOAS. We do see some hot water heat. I believe that we'll see a migration as we see strategic electrification and all-electric building design start to take hold in places other than New York City and Boston and California. I think we'll see the DOAS systems gravitate from gas-fired heat to heat pump heat. So you can today select DOAS systems. Manufacturers can build those units with heat pump coils and heat pump condensing units built in. So I think we don't see that many of those today. I think over time we'll see a gravitation towards the heat pump technology in the DOAS system also. Option number 5, we can take the outdoor units and install them inside the building. This was somewhat popular early on when VRF was brought to the United States in the early 2000s in the extremely cold states like Wisconsin and Minnesota and North Dakota. You take an air-cooled unit, put it in a mechanical room, and then I'll show you on the next screen what that looks like schematically. But essentially, not only are we getting the equipment out of the weather, so it's easier to work on, it's not being snowed on and rained on and hailed on, but we're turning the mechanical room into either a mixing plenum or a recirculation air plenum or a pass-through air plenum, depending on the outside temperatures. So I think the next screen will show what I'm referring to. So here we have that air-cooled outdoor unit shown in the middle of the picture, and we've got an outside air louver or intake louver on the right-hand side of the room, and then an exhaust air louver on the left side of the room. So whenever it's warmer out, we have both the outside air louver and the exhaust air louver open, and essentially it's just a single pass through the mechanical room. So the mechanical room is essentially the same temperature as outside ambient in this instance. So the air is coming through the outdoor air louver, passes across the condenser coil, goes up through the unit, the condenser fan pushes it out the exhaust air louver through that ductwork that is shown. So that would be at more mild temperatures. As it gets colder and drops below a certain temperature, we then would close the outside air louver, close the exhaust air louver, open up that recirculation air damper that's shown, and now our mechanical room becomes a big recirculation air plenum. And then we're going to use that unit heater that's shown to heat that room. And by using the unit heater, typically gas or maybe hot water, as we use that unit heater to heat that room, that heat then gets absorbed through the condenser coil and gets transmitted into the building by the VRF system. So you get the additive nature of the unit heater heat and the VRF heat added to it to heat the building. So it's one nice central location to put your auxiliary heating equipment. This is essentially, you've got one spot now instead of putting duct coils or baseboard radiation all over the building, which can get costly if it's not already there as part of the infrastructure. It's one central location to put that equipment. We're seeing this less and less because it's fairly expensive. You can imagine all those dampers and louvers and operators and the controls required to operate that. We're seeing this less and less and seeing more of the flash injection take the place of this design. Lastly, option 6 would be using a water source VRF system. Nice thing about water source VRF systems, similar to what I just showed you with placing the air-cooled units inside the building, the water source VRF system, everything is inside the building, at least everything from the VRF system standpoint. You're still going to have some sort of heat rejection device like a cooling tower or a fluid cooler. But the equipment, the VRF equipment is installed indoors, so it's not getting rained on and hailed on and animal infestations into the equipment, things, building nests, things like that. So equipment generally will last at least 5 years longer. You also get better performance and better efficiency because you have a water loop which you're rejecting heat into or pulling heat out of depending on the mode condensing unit. But that water loop is a much more defined temperature range, generally between about 60 degrees Fahrenheit and 90 degrees Fahrenheit. So it's real similar to a traditional water source heat pump system. If the water loop gets below 60, you turn on a boiler and you heat the loop up. If the water loop gets above 85 or 90, you turn your fluid cooler on, pull the loop temperature back down. So the VRF condensing unit's not seeing, temperatures that range from 10 below zero to 95 degrees Fahrenheit. It's seeing a much more controlled temperature. Plus, it's easier to pull heat out of and reject heat into water as compared to air. So that's why you see some efficiency increases. And you can get water source VRF systems just like the air source in either a heat pump changeover system or a heat recovery system. Just a schematic showing that. One thing to keep in mind with water source systems, it has to be a closed loop system. So we show a cooling tower there with plate and frame heat exchanger. You never would want to just run cooling tower water through the water source condensing unit. It would get fouled up fairly quickly and derate in performance very quickly. So you either want a cooling tower heat exchanger combination or a closed circuit fluid cooler. And then, like I mentioned earlier, the boiler to temper the loop as it drops below the predetermined temperature of, usually around 60 degrees. So a few other installation considerations. We always want to get the condensing units or outdoor units mounted up off the ground on an open stand. Typically, we want this to be at least about 12 inches above, whatever you expect the snow depth to be. 18 inches is kind of a common height that we see. You want to make sure it's open so that snow doesn't drift against it. The snow would just blow right through with the open stand. You also want to give some consideration to what happens when this unit goes into defrost and that water basically sheds down the outside of the unit where that water goes. So you want to make sure it's not a nearby sidewalk that is hindering egress into the building. You don't want people slipping and falling on the sidewalk because the condensate water sheds off the unit and then refreezes on the sidewalk. So just some things to think about. This high wind conditions, if you have a unit or units that are up on a roof and they're exposed and they just catch the wind, if you have low ambient kits like is shown there or snow hoods, these things get pretty tall and have a fair amount of surface area, so you want to make sure that you support them properly with guide wires. If they're outside next to the building and protected by the building itself or fencing, you generally don't need this, but this is where you have exposed locations. You want to make sure that the units are secure. Snow hoods and hail guards are a good idea depending on where the units are mounted. Those two units there, the one on the left has both the hail guards installed and the snow hood installed. Probably wouldn't install those in this application because it's got a roof over it. Generally that's for areas where it's open to the weather. They do improve defrost efficiency, we found. We don't include that in the ratings, but we know that the units perform better when they have these cold weather accessories like snow hoods and hail guards installed. Also, the snow hood is handy for if you're installing the units under the drip edge of the roof, which is a common location. We see that all the time. And then in winter, you get those icicles that can be, 2 feet long and 2 inches in diameter. And then in the spring, they break off and can come down through the condenser fan and destroy the condenser fan. The snow hood would prevent that. So planning for winter, as I said, keep equipment above the snow line. Think about defrost, where that water goes as it melts during the defrost cycle. Drain it away from sensitive areas where there could be slip hazards. Panel heaters, base pan heaters are accessories. They're oftentimes built in as standard on the purpose-built flash injection product, but on the standard products are usually also available as accessories. And then, as I mentioned earlier, exercise caution, putting the units under the drip edge without any sort of protection from damage. So there have been a lot of field third-party studies done that show that VRF is very effective in cold climates, especially if you have a goal of decarbonization. The Minnesota Department of Commerce, Division of Energy Resources, put out a report in 2015 that showed that this was a very effective technology even in cold climates like Minnesota. And that was 5 years ago. And we've seen significant increases in heating output and performance in those 5 years. So generally, as we release product, it gets more efficient, better heating output, and oftentimes a smaller footprint. So with that, I'm going to turn it over to James to talk about a few case study projects.
All right, thanks a lot, Mike. That was a lot of great information on installing VRF in cold climates. I know we want to leave some time for Q&A at the very end, so now that we've talked a little bit about getting an understanding of VRF technology and look deeper into opportunities for cold climate applications, I wanted to spend just a few minutes and look at a couple of real-world examples where applying Mitsubishi Electric VRF systems resulted in superior energy efficiency for buildings. The first case study I'd like to share with you is Minnesota Power. Located in Colquitt, Minnesota and Upper Minnesota, it's actually about a couple of hours north of Minneapolis and just west of Lake Superior, so it's really a very cold climate area. Their company headquarters is a 5,000 square foot office building. The company prides itself on helping the state reduce reliance on oil and natural gas. They were able to retrofit the building and replace a faulty HVAC system with the desire to promote strategic electrification and demonstrate the efficiency of VRF systems. As I mentioned on the last slide, this is a very cold climate area with a low ambient design temperature of -20 degrees Fahrenheit. Based on 30-year averages, design temperatures only occur during 1% of all hours in a year. This challenge was solved with heat recovery system equipped with hyperheating technology and auxiliary heat. Minnesota Power is now an example of a highly efficient, sustainable heating and cooling facility in its state. Minnesota Power has a conference room where they've installed 2 individual thermostats side by side to demonstrate how heat recovery works. Each thermostat is connected to a separate indoor unit and lights up either blue or red for cooling or heating. The next example I wanted to share with you is the AC Marriott Hotel. It was built in 2017 and located in Dublin, Ohio. It's a 140,000 square foot, 8-story building. Now, Dublin is an affluent suburb of Columbus, Ohio, and it's home to several Fortune 500 companies and hosts the renowned Jack Nicklaus Memorial Golf Tournament. We're starting to see a shift toward VRF within the hospitality market. The big reasons are energy efficiency through heat recovery, maintenance, comfort, and acoustics. When guests stay at a hotel and hear a conventional system kick on, it may annoy them or even wake them up in the middle of the night. Quieter VRF systems provide a much better experience for guests in terms of acoustics. VRF systems provide much better comfort in terms of temperature and humidity control. Again, unlike conventional systems that constantly turn off and on, a VRF system runs continuously and efficiently while also adjusting fan speeds to continuously remove moisture. Now, the general manager of the hotel, Mr. Orkun Turkay, commented, quote, "The most important thing for our hotel guests is that HVAC operation is simple, comfortable, and unnoticed." The hotel was originally designed around a water source heat pump system based on its efficiency and individual room control. The developer brought Mitsubishi Electric into the project to look at the variable refrigerant flow water source systems just before the bid was about to go out. The developer liked the technology, especially the equipment and installation savings of over $500,000 versus the original specified heat pump systems. Now, I know Mike talked about this, but the advantages of water source VRF system in extremely cold climates include the fact that with water as the heat sink of all the VRF systems equipment, they can be installed indoors. Indoor installation means the equipment is better protected from outdoor conditions and can deliver optimal performance and even lower degradations of performance in extreme cold. So with harsh winters and temperatures that dip below freezing, water source VRF help improve the guest experience for the AC Marriott. Now, a few takeaways from today's webinar. Modern VRF systems offer cold climate capabilities far beyond older systems. With flash injection technology and today's compressors, VRF systems perform reliably in climate zones 1 through 6. Some systems provide heat down to minus 31 degrees Fahrenheit. We talked about some of the challenges of cold weather climates and the use of flash injection technology, auxiliary heat, DOAS systems, indoor installation, and water source systems. We talked about preparation for cold weather, which includes installing outdoor units above the snow line, using snow hoods, as well as following best practices, and staying current on how manufacturers are moving VRF technology forward. And finally, VRF systems are positioned for growth and wider adoption as decarbonization and strategic electrification gains momentum. The cold climate performance of VRF systems make these initiatives feasible and solves challenges for building owners. That concludes the prepared portion of today's webinar. Mike and I enjoyed discussing VRF technology and the opportunities for applying VRF in cold weather climates. We hope you found the information to be valuable, and we look forward to answering your questions in just a few minutes. If you'd still like to submit a question, please do so through the Q&A interface within the webinar. But first, I did just want to highlight a few resources, among many others, available for your use after this presentation concludes. These resources include our website, metahvac.com, metahvac.com. Also, there's a link to our quarterly engineer, architect, and facility manager newsletters. In addition, we've also included a link to our case study library where you can explore how VRF is applied in a variety of applications. There's actually over 170 different case studies within this link, and it includes every application from hotels to office buildings to education facilities and many others. And lastly, a link to locate a qualified HVAC contractor or VRF distributor. On behalf of Mike, thank you again for your time and attention today. And with that, I'll turn the presentation over to our Q&A moderator, Andy, to begin that portion of today's webinar. Andy?
Thank you, James. Thank you, Mike. Great presentation. We have more questions than we will be able to answer, but let's get started. So this first question is with regard to something we haven't talked about much, which is cooling. At low temperatures, can we still get cooling out of the VRF system for interior zones?
Yeah, I know. I'll let Mike respond to the majority of that question, because I know he's up in Ohio and has to deal with a lot of those cold climates, and we talked about a little bit about how the low ambient kit works. So Mike, I'll let you explain a little more about that.
Yes, the short answer is yes. The long answer would probably take half an hour to explain. Generally speaking, VRF systems can provide full cooling for any indoor unit down to 23 degrees above zero Fahrenheit. And with the low ambient kit, we can take that lower, usually between 0 and -10. However, there does need to be caution exercised, especially with air source VRF systems, in dealing with process loads. So if you have process cooling loads that are totally independent of outside ambient, in other words, your load could be 100% if it's 5 degrees below zero outside, there are considerations there, design considerations that you have to look at. We have a white paper or application note put together that addresses that topic. So the short answer is yes. The long answer is, it depends, and you need to look at the specifics.
Okay. All right, great. So for some of these questions, we're going to consolidate them. So there were a number of questions related to installing outdoor units inside. So if you install outdoor units inside of a building, how do you size the additional unit heater, and how does it communicate with the outdoor unit to, if, let's say, the outdoor unit is experiencing a temperature that makes it difficult to maintain the zone set points?
You want me to take that one, James?
Sure, yeah, go ahead.
So generally, unit heater sizing, you can look at the total block heating load of the building and size the unit heater or unit heaters for that load, less any credit you would get from the VRF system. Generally speaking, your VRF system is going to be smaller because you're going to be switching over to that auxiliary gas heat at a certain ambient. And we've written sequences, and once again, this is covered in an application note that you can download on mylinkdrive.com that goes into these details. But generally, usually you see the room be maintained at either 40 degrees ambient, in which case you wouldn't be running the VRF heat pump heat very much and be switching to that auxiliary heat source quicker. Or there's another sequence of operation where we go all the way down to 20 degrees. And either of those temperatures are adjustable. You could make that whatever you wanted. Whereas if you run the room all the way down to 20 degrees before you close the outside air damper, close the exhaust air damper, open the recirc damper, you have to make sure that the room is winterized at that point, because it's going to be seeing temperatures well below freezing. So there's some sequences that can determine when you shift from VRF heat pump heat to auxiliary heat, and that's totally up to the designer to determine how you want to do that. But the easy thing, sizing the unit heater, is to take the block heating load of the building and take a credit for whatever VRF heat is going to be added at that temperature. Gas unit heaters are pretty inexpensive, so if you want to put in, two 800 MVH heaters versus two 600 MVH heaters, your incremental cost is very little at that point.
Okay, great. This next question is with regard to one of the methods for addressing derating. which won't oversizing to heat capacity significantly reduce the turndown capacity during part load cooling and heating conditions?
You want me to take that, James?
Sure. Yeah. Go ahead, Mike.
Generally, when you're oversizing, it's not that much. You might be bumping up like one nominal size. Maybe you go from a 20-ton nominal size system to a 24-ton. So your low-end turn down is pretty good on most units. It usually goes down into the, below 10%, usually between 5 and 10% for your turn down. So you're not really affecting the turn down very much. So it's not like you're doubling the size of the condensing units. You're usually going up maybe one incremental size.
Okay. Next question. Is there a way to sub-meter or separate the electrical use of the outdoor heat pump for different tenants?
Yeah, I'm not sure if you've worked on some of those projects in the past, Mike, but I know there is energy allocation type software that we are able to go back in and see how much energy is used per unit. I'm not sure if any of the projects you've worked on entail that or not.
Yeah, that's pretty standard practice, fairly easy to do. We do that quite a bit, where we can actually use watt-hour meters and measure the current coming into the outdoor unit on a real-time basis, and then knowing what each of the indoor units connected to it is doing, we can allocate that energy quite accurately for different tenants. So we do that quite a bit, especially on multifamily applications.
Okay. Next question. So this person says, first costs are always an issue when we consider VRF systems. How typical is your Marriott example?
In that case, there was some other considerations on that building design that helped lower the cost. They had boilers up on the 8th floor mechanical room, and they were pumping hot water all the way down to the first floor to serve some wall-fin radiation, which served a big glass curtain wall. So we were able to use our booster units, which is a VRF indoor unit that makes hot water, and eliminate a lot of that piping throughout the building. So there are some other considerations on that project. Generally, we see VRF systems being a little bit of a price premium to most unitary systems, so packaged rooftops, VAV rooftops, certainly PTACs and split system furnaces. But we usually see it being a price deduct compared to most applied systems like 4-pipe, chill water, hot water systems, certainly chill beams, geothermal systems. So it really depends on what you're comparing it to. We have found it to be generally in the same ballpark as water source heat pump systems. The AC Marriott had some unusual circumstances that helped VRF look even better. But generally, we see that compared to traditional water source heat pump systems, VRF is usually a little bit less expensive, but kind of the same order of magnitude. So a lot of it depends on what the conventional system is that it's being compared to.
All right, next question. What is the max number of devices for each branch box?
Well, the one thing about we talked a little bit about the branch circuit controller, I assume is what the question is going to. You actually have a main branch circuit controller, and you can connect multiple sub-BC controllers to the main BC controller. And one of the interesting things about our latest generation of product is the line lengths have increased by over 130 feet that you're able to run the piping from the flooring. Mike, I don't know if you want to add anything on that.
50 is kind of the magic number that you can put on one system. We rarely see 50 indoor units on a single system. I don't know that I've ever seen it. Generally, it's usually between maybe about 5 and 15 is kind of a common number of indoor units you see on a single system. But you could, with multiple BCs, and as Jim said, use BC controllers, you could have up to 50 indoor units on a single system. We just don't really see it.
All right, so this will be the last question. We have a lot more we could ask, but you have to wrap this up. So, how long will it take a system to warm up to set point after a 5, 10, or 15 degree night setback if the outside air temperature is below 32 degrees?
Mike, I'll let you take that one.
Yeah, we don't see too much problem catching up from night setback at 32 degrees. Now, once you get below 0, that's a little bit different story. I'm one that likes to keep it simple, both the design and operation. And I've always told people, I live in Ohio, and we design for 0, but it gets colder than that. I always tell people in the winter months, so December, January, February, if you want to keep it simple, maybe set your building back 3 to 5 degrees, and you shouldn't have too much trouble catching up in the morning. Where you get into trouble is if you're setting back 8 to 10 degrees and it's 5 below 0 and it's a school building, and you can maybe get the air temperature back up to 70 degrees by the time class starts, but I can guarantee you're not going to get all the mass in the room back up to 70 degrees. So the cinder block walls, the tile floors, the desks, all that mass is not up to the same temperature. So it's still going to feel cold. So you just have to be careful with night setback. You can do it. You just don't want to do it too aggressively in the really, really cold temperatures. But we don't see much problem at, temperatures in the, the 20s and 30s catching the building back up. I would never go 15 degrees of setback, but 10 would not be unusual at those mildly cold temperatures.
All right, thanks, Mike. Thanks, Andy. I did want to just briefly mention one other resource. I believe Mike mentioned it earlier, but MyLink Drive, MyLinkDrive.com is another great resource for information. It has product overviews, product specs, indoor units, outdoor units, accessory information. So that is one additional resource that you might want to take a look at. But again, thank you, Andy. Thank you, Mike, for your time today. We appreciate everyone's time. We hope you found the information useful, and on behalf of ASHRAE Journal, thank you for joining us, and have a great day. Thank you.